Assalamualaikum. My name is Nur Atika Akila binti Amruddin from 80228-2A. Now, I would like to present about detection of NPK nutrient using fiber optic sensor. This slide contains introduction, description, explanation, elaboration, conclusion, and reference. The principle of optical NPK sensor is based on interaction between incident light and soil surface properties, such that characteristics of the reflected light vary due to the soil physical and chemical properties. Laser-induced fluorescence spectroscopy or near-infrared spectroscopy technique or UV spectroscopy is widely used in experimental and commercial purpose. It is reliable but time-consuming, complex, and high cost per test. This diagram shows that NPK sensor is built using multi-mode plastic optical fiber. Various sensing configurations have been reported for chemical sensing. The color of a substance caused by the absorption of light wave of specific wavelengths. The absorption of light by solution results in excitation of electrons in its molecule. The different color LED emit colored light of same intensity. Light is incident on the liquid via multimode optic fibers. A reflector is placed at an optimal distance. Different intensity will be received for different colors as light travels through the solution from the probe to the reflector and back, depending on the color of absorption characteristic of the solution. To obtain a fairly simple absorption spectrum at discrete wavelength, plot the reflected intensity against the wavelength of the source. From the obtained spectrum for the various soil sample aqueous solution, a simplified detection mechanism is developed. This illustration shows how fabricated NPK sensor working. Next is how it works. This block diagram shows of NPK detection. Reflected light is collected by the probes receiving fiber and converted to an electrical signal via a phototransistor. The sensor output is calibrated using the standard color chart deficient component values. The sensor's electrical output varies with the color of the solution. The signal conditioning circuit is made up of buffers, an inverting amplifier with variable gain, and an op-amp based subtractor with a zero setting. Values of the NPK deficient component are predicted by comparing current values obtained with the microcontroller database, and the LCD displays the name of the deficient component as well as the amount needed in the soil, so that the user can choose which fertilizer to apply to the soil. Next, we continue with the experimental procedure. For preparation of solution, aqueous solution of soil samples with known NPK values are made by adding water to the soil and precipitating it. The NPK values are verified using market standard kits, green-field soil tester in conjunction with the universal indicator and standard color charts. The aqueous solution that remained above the precipitated soil was used for measurement. And the color of aqueous solution for the sample shows pink for phosphorus deficiency, orange for potassium deficiency, and gray for nitrogen deficiency. For the measurement, initially the distance between probe and the reflector is varied, and the output for each distance is recorded. It is discovered that a probe to reflector spacing of about 2 mm between curve corresponding to different value of NPK is optimal. As a result, it is decided that all future experiments will be conducted with the separation set at 2 mm. This graph shows the optimization of distance between the sensor probe and reflector as 2 mm. And then the experiment is then carried out with the other soil samples. The fiber optic NPK probe is immersed in a chemical cell containing aqueous solution of various soil samples. Because the color of the solution is determined by the NPK values, the final reading provides information about NPK values. The graph shows the result from the experiment. As we can see, for nitrogen test, X value is 14. The program's low nitrogen threshold value is 15. The comparator color corresponds to the value of 420 kg per hectare, which is low-medium for this soil sample. So, this soil needs nitrogen. Next, for phosphorus test, X value is 33. The program's medium phosphorus threshold value range from 20 to 35 because there is enough phosphorus in the soil. And lastly, for potassium test, X value is 55. The program's high potassium threshold value is 50. The potassium content of soil is extremely high. It indicates that potassium fertilizer is no longer required in the soil. In conclusion, a fiber optic sensor is thus developed to detect nutrient deficiencies in soil such as N, P or K. The sensor is built with concentric source and receiving fiber arrangement. It is based on the colorimetric principle, which states that the absorption of light by the solution causes a variation in the sensor's output. The system thus designed is advantageous because it reduces the unnecessary use of fertilizer in the soil. One can properly select the amount of fertilizer to be used to reduce soil deficiency in a specific field. This is the reference I use for this presentation. That's all for me. Thank you for listening.